All right. Thank you very much for this invitation, for the kind present as well. I just tried to get the last drops of coffee I had, which is fighting my jet lag, which is like in the peak at the moment. And the gift is especially useful from the point of view of mathematics development as well. You will see why, hopefully, by the end of this talk. This nice 3D structure we have in this envelope. So, yeah, the talk will be about mathematics development in general, which is summarizing a large part of our research at the Center for Neuroscience in Education in Cambridge. So this center was set up actually about 11 years ago, exactly when I went to the university. That's why I went, actually, to help setting up this center. So my background is in cognitive neuroscience and psychophysiology, but I drifted into the education field. So I'm doing lots of interdisciplinary research basically on the neuroscience of educational phenomena, on the cognitive psychology of educational phenomena, on educational phenomena per se. So it's really a mix of research what we are doing. And we also work with adult learners as well in this Center for Neuroscience, just to test models of learning and development in general. So we have a very wide scope of studies, basically, at this center. And so let's see, what is mathematics? This may not be very trivial for adults, but mathematics is because you are kind of used to doing some kind of mathematics. Because mathematics development and mathematics learning is extremely complex. So math, basically, and that's one of the message here, which is important to understand, math can't really be designed as one thing. It is a collection of lots of things. It relies on lots of cognitive phenomena. So it is something incredibly complex, and perhaps more complex than lots of other things children have to learn in schools. And this complexity is very easy to get forgotten if we don't actually externalize it. So basically, you have to learn about, and imagine that you are a 5-6-year-old child who just gets into the school and everything is new for you. So you have to get familiar with all these incredibly complex bases of mathematics. So you have to learn, can you hear me if I turn this way as well? Yeah? Okay. So you have to learn about magnitude and quantity relations. So what is small, what is large, what is few, what is many. These look trivial concepts for us adults, but for children, probably not, or we know it from the research literature that these are not necessarily trivial concepts. So what is more than something else? What is a little bit? What is not a little bit, and how much less a little bit or more a little bit? So these can be really confusing concepts for children. You have to learn all of these. And you have to then learn associative series, which means early verbal counting, which again relates to symbols. You have to learn what is 1, what is 2, what is 3, and how these come in succession, and what is the relation between them. So we get to the concept of ordered series. We have a certain quantity, we have a larger quantity, and you can continue this ordered series indefinitely. You have to understand that it's indefinite, it can just go on. You may not know the labels, but you can still continue. Even mathematicians, very good mathematicians, were struggling with the definition of number line, for example, at the end of the 19th century and probably in the early 20th century as well. But if I'm right, only towards the end of the 19th century could mathematicians properly define number line, for example, as such. Yes? So these are not really intuitive concepts. They are intuitive to a certain degree, but beyond that, you do have to learn a lot of things to be able to understand these concepts properly. You have to associate quantities with elements of series. So if 1, 2, 3, 4, 5 come in succession, children may be able to use these series just like without much understanding, but they have to realize that certain quantities link to certain verbal labels, for example, and these quantities have relations to each other as well. So there are several layers of understanding here already, And the number line is a kind of visual spatial representation of the same series you may have learned verbally. So you have to understand how visual spatial concepts relate to verbal concepts, how they relate to magnitude. So not one thing, even the number line concept includes lots of different elements of learning, but these look very natural to us because we may have undergone a very long-term development in school, so you already have like lots of years of schooling behind you where you pick up these concepts, but imagine that for children these all are new. And associating magnitudes and number line parts, let's say with space, another step here. And if you think about the extended number line, then come concepts like zero and negative numbers. Negative numbers were unknown to the Greek mathematicians, for example. They couldn't even accept the concept of a negative number. They thought it was a meaningless thing to think about negative numbers. But currently in schools, we already expect probably 10-year-olds or even younger children to understand negative numbers and the concept of zero, whereas even the best Greek mathematicians were struggling with these concepts. So can children really understand these conceptually, or do they only have a mechanistic view of them? It's a very interesting thing. How can we expect children to cope with something which even the best mathematicians way back couldn't really grab conceptually? So it's not only a mechanistic, codified piece of knowledge, but conceptual understanding is important here. And of course, the quality of schooling and education is important. Teachers must understand these concepts properly so that they can actually explain it to children. If you have a particularly demanding, let's say, gifted child in the classroom, then they may be able to confuse teachers quite a lot with their uncomfortable questions. If anybody who taught children may have come across such questions. So the teacher's subject knowledge has to be very precise and firm so that they can actually explain these concepts properly. And then if we come to language, then lots of numerical facts are stored in long-term memory. So children have to learn the multiplication table, for example. If they want to work efficiently, then they can't really rely on ongoing computation at each moment to compute these products, for example, but they have to memorize them. So there is a lot of work here, a lot of long-term memory retrieval. And also, they have to learn syntactic elements relatively early in primary school. So, for example, the preference of operations, this series is very, or this operation series is very simple here. The numbers are very small, but you can see that you do have to put in some work into resolving all these signs. You have to interpret syntactically this particular mathematical sentence, even if it's just very simple. And so you have to learn about preferences, embedding, operation signs, operators. This is all mathematics. Yes, this is, you can see the point that it's not one thing. You learn a lot of things so that you can do even elementary mathematics. And then the concepts and logical elements are important. So we already mentioned zero and the concept of continuum. And then you have to understand these kinds of logical structures here. You can use this kind of equations to test whether children really understand what they are doing, or they are just mechanically following what they see, or they realize very simple rules in a text problem or in a written algebraic problem. And visual spatial abilities, we already mentioned them in relation to the number line, but of course they are important when you want to understand place value. So the whole place value system, which is underlying modern mathematics, relies on kind of a spatial representation, spatial understanding. It is organized spatially, and that's one of the reasons it is so efficient in solving problems. So you can see that these can be tricky for children even, or indeed, typical errors involve just omitting zeros from particular place value positions or inserting wrong digits in particular place value positions. So these are all reflecting where it's important to put in more learning effort. And then operation techniques are relying on spatial manipulations often, so you can use space very efficiently to solve these kinds of problems. So again, spatial augmentation in relation to place value, which is another spatial system in relation to understanding of magnitudes, in relation to understanding series. Everything is represented even in this kind of very simple operation here. So I'm emphasizing this complexity so that you can see what may be mathematics. Of course, if there are mathematicians present, then they could argue probably endlessly more about what is involved. And then if we go further, then Partwhole relations are important, for example, with regard to fractions, which is an extremely confusing domain for children initially. So fraction learning is a very tough thing for children, and then you have to learn very strange operations, which seemingly are very strange when they get into the fraction domain. So these seem to be fairly independent to them from normal operations or normal numbers, so they get confused very easily by these operations initially. And then story problems, they have to form an abstract model, basically, of a text problem of real life. So they have to know how to conceptualize this text problem, how to model it, how to translate it into numbers. That's kind of another skill which is required in math learning. So you can practice here. And you can recognize that there is a huge memory load involved in solving these kinds of problems. So if you came across very talented math people, then you may be struck by the number of elements they can memorize seemingly instantaneously, and they just use all of them to model what you are saying to them. So they keep everything in mind, they organize it in a structure, they are able to retrieve it, they are able to operate on it. So obviously, they have to rely on the memory and use it very efficiently for problem solving. So memory is not per se involved in the mechanisms of mathematical problem solving, but it's an extremely important skill they have to develop so that they can actually solve problems. You may know the feeling when you have the impression that you know how to solve a problem, but you forget some tiny elements of it, you confuse a sign of a number, you end up with a completely wrong result. So these may be all very little memory problems, memory errors you make during solution, but because these memory solutions are able to result in a completely bad mathematical outcome, they are extremely crucial for carrying out mathematics, even if they are not mathematics per se. So math is incredibly complex. That's the math message here, and we could continue this list, what's required for mathematical problem solving even in primary school. So it falls back on various cognitive functions, and all of these cognitive functions are needed for efficient mathematical problem solving. And obviously, if we require children to solve mathematical problems efficiently, then we have to develop all of these necessary background cognitive functions in them. And you can have some kind of intuition about these functions. For example, long-term memory is important so that you can recall and memorize mathematical facts. For example, in the case of the multiplication table, short-term memory, verbal memory is important as well. When you solve an equation, you have to memorize partial outcomes, you have to memorize parts of this equation, you have to translate a story problem into a formal system, so to say. So you have to keep all of these partial results in mind. Visual spatial memory is extremely important because we use number lines in problem solving. So you can imagine operations, and visualization may help you to keep things in mind in general, have a spatial model of things. Attention is extremely important. Again, you have to stay focused on that particular problem. You have to direct attention to parts of a problem. When you have to resolve a certain syntactical structure of a problem, then you have to focus, let's say, on what's between certain parentheses. You can't start problem solving in the wrong place. it's not efficient, let's say, or it will lead to some kind of a wrong result. So attention is important, just like even in focusing attention within a particular mathematical structure. Suppression of unwanted information may be very useful, resisting distraction, not only from classmates, but also from irrelevant parameters in a problem. They may be there in a text problem, for example, but they may not be important for a solution. You have to neglect those when you build a model of a text problem, even in case of a relatively simple text problem. Actually, I know that some very user-friendly math course books may actually be too distracting. When I was looking at them, I found that they, let's say, just have too many images. So the children tend to look at these images and not actually think about the problems. But they may be very good to train resistance to distraction. And then general processing speed is important because usually mathematics is examined under time pressure. So you just can't linger on, even if you really enjoy problem solving, you just can't do it for hours and hours and hours. You have to come up with a solution in a certain set amount of time. And this is a good skill to be trained because that's required in real life. Unfortunately, we can't enjoy thinking about a beautiful problem for days or months, even if I like to occasionally, but I have to get on and solve another one. So this is an important skill to train, and it's very important in math problem solving in general. So already we can list various cognitive functions which are obviously very important for mathematics, and in order to do even just successful primary school level mathematics, you need all of these. You can't really simplify the situation to one skill or one crucial, so to say, I would say, to one crucial core skill of mathematics. There is no such thing as a center of mathematics in the brain. You have to, in my view, you have to train all of these important cognitive functions so that you can actually cope with even simple level mathematics. And then, after this conditioning that math is really complex, we come to the concept of developmental dyscalculia. But this complexity is important to consider also for understanding what's required for normal mathematics development. But in the case of developmental dyscalculia, we talk about weak mathematics development. So if you think about the normal distribution, then it's kind of logical that by definition it affects, dyscalculia affects around 6% on children and adults. This only means that around 6% of children and adults can be categorized as being very weak relative to their peers in math learning, basically. And what we require is that this is defined as kind of a selective weakness of mathematical learning. Oh, I thought it was some announcement. But selective weakness of mathematical learning, and this means that intelligence and reading and motivation to learn mathematics should be in the normal range, and access to appropriate education and provision should be normal as well. So it's not that these children are generally weak, and it's not that they don't have access to proper education. They may have access to good education, and they may even be motivated to a degree. It's not that they are lazy, but they are just not coping with proper mathematical understanding. There is no generally accepted functional definition of dyscalculia, so we wrote a summary review about this very recently. That was automatic. So this is actually a special issue on developmental dyscalculia, which we edited, so it has numerous papers about it if you want to learn more about this condition. So there is no generally accepted functional definition of dyscalculia. We don't know whether it's a simple, multiple, or heterogeneous problem, but if you think about the complexity of mathematical learning, then it's highly likely that numerous factors are involved in dyscalculia. And so it also means that we do not know exactly what cognitive functions are deficient or weak in developmental dyscalculia. This whole talk will lead to some. And we also are not sure at the moment what are the actual subtypes of developmental dyscalculia. That is, can we categorize children with weak math understanding further into subgroups? We do not have a clear subgrouping at the moment. So current research, and this is really kind of new research, focuses on the functional understanding of dyscalculia, so understand what kind of causes developmental dyscalculia. And then we went through the complexity of mathematics learning before for a reason. So if you think about all that complexity, then we can have the hypothesis that it's extremely likely that developmental dyscalculia can be related to the weakness of various cognitive functions. I don't think you can relate it to knocking out one part of the brain, let's say, or just one element of learning. If math is so complex, then numerous aspects of this learning network may be affected, perhaps in some cases, and various weaknesses of this huge network of learning may result in weak mathematical understanding. So we've seen that memory, attention, cognitive control, inhibition or suppression of unwanted mental acts all are important for mathematical learning. So in principle, we could expect that any of these functions could be implicated in developmental dyscalculia. So again, if you think about solving this very simple problem here, if you just try it, then you see it's not trivial. Yeah? We only have very small numbers here. It's all under 5. You could expect a primary school child to solve this equation, but even for adults it's not that unless you are an autistic genius. Anyone? It's not instantaneous, it's not like flash. You have to organize how you do this very simple problem solution here, even if it's, so to say, trivially easy. So that is, I think, a good example to demonstrate that you do rely on lots of skills, even in just solving something simple like that. So currently we have various projects then to study mathematical learning and study the basis, the functional basis of developmental dyscalculia. So we try to understand this, and we also study mathematical expertise in normal children, obviously, which is important to understand the functional basis and to understand how gifted children may be different from normally developing children or dyscalculic children, as they are excellent models as well, so to say, of outstanding mathematical learning. So working with gifted children is pretty important as well. Two different?
Yeah, I say 9.
Here. Okay, we can discuss that after. I have a unique solution. You mean it's ambiguous? Or?
It's ambiguous.
Oh, this one. Not in my view, but maybe because I'm used to computers. They have very strict priority orders, so that's one of the things here. What's the priority of which operation? What's that?
It's not an equation.
Yeah. Okay, not in the strict sense. All right, you see what excellent discussion you can have just about this piece of work here. That's already very exemplifying, I think. All right, so one of the things we can do when we try to understand dyscalculia is, of course, making very nice images of the brain, which may be useful from certain points of view. And one of the nice imaging tools we have is structural MRI. So I just included some of these introductory slides here because I expected very varied audience. I guess this is the case. So structural MRI gives a three-dimensional view of the brain. So you can see here various brain parts, basically, so you can literally look into the head of people and study, for example, how much gray matter, how much neuronal volume we have in the brain, and you can also study the pathways of the brain, so what kind of connections we may have between the neurons, which are basically the processing elements, the processing computers in our brain. So this is one helpful thing to have, and another important tool we have is functional magnetic resonance imaging or functional MRI, which examines blood flow in the brain, basically. So it examines how much oxygen is consumed in various parts of the brain. So it gives like an indirect view of brain activity. So it doesn't reflect neuronal activity, it gives you an impression of oxygen consumption in the blood, basically. Yeah? And for example, if you have this rough anatomical image here, you can overlay the oxygen consumption image on this, and this picture could be interpreted in this particular case as demonstrating higher levels of brain activity in these particular parts. I'm talking in general terms here. Okay, so functional MRI is another tool we can have, and then when we exploit these tools for studying dyscalculia, little break, then we can see an interesting picture. So in this particular study, people used structural imaging to depict the brains of dyscalculic children. So in 2009, so relatively recent. And then they examined, the researchers from Stanford University examined how the brains of dyscalculic children differ from the brains of control children. And all these, so you can see a general images of the brains here, at different anatomical segments or slices of the brain. And then wherever you see these colored parts, that shows a difference between the brains of dyscalculic children and control children. What is to be noticed in this image is very simple for our purposes now, is that these differences are basically all over the place. So they are extremely widespread. When you compare the brains of dyscalculic and control children, then you can see numerous differences between their brains. And if you think about the complexity of mathematical function I was arguing before, then you could expect something like this. If math is so complex and dyscalculic children and non-dyscalculic children can differ from each other in many ways, then you could expect something like this, that is widespread, very complex differences between their brains. So it's not just that they have a difference in a very tiny part of the brain, but they have differences very all over the brain, so to say. So this can, again, suggest that we can have various underlying functions which may be different between dyscalculic and control or normally developing children. Yeah? And again, so this complexity could be exemplified from those brain structural images as well. So we started a large project on developmental dyscalculia, starting on the basis of what I just argued before, that there could be numerous differences between control or normal developing and dyscalculic children and their brains, obviously, so their brains being a reflection of their mental function, so to say, if we think that the two are interrelated very tightly to each other. And our hypothesis was that you can't really distinguish between these children just focusing on one thing, so we have to measure lots of things and compare lots of things in these children so that we can identify exactly what group of functions may be different between control or normal developing and dyscalculic children. So we did this study between 2009 and 2012. This was funded by the Medical Research Council of the UK. And so it was a very detailed and long investigation. So we involved more than 1,000 children. You can see how important that more is there and how relevant 1,000 versus 1,004. I'm very proud of that more. Thanks to my excellent colleagues who are just testing day and night. So we imaged, or examined, not imaged, more than 1,000 children in year 3 and year 4 of primary school. You can see that we had lots of boys and girls, so the gender ratio was about 1:1. In this particular sample, this is kind of the biggest such investigation in the UK ever done, actually. We worked with around 22 schools in Cambridgeshire, Hertfordshire and Essex in the UK, and